Hello, eighth graders. Today we're talking about volcanoes at plate boundaries. So this is chapter 8 in our Tectonics iBook. Chapter 7 was about tsunamis. So the last few chapters of this book are about volcanoes. And volcanoes are, we know them as very dangerous, disaster creating objects on Earth's surface, but we also recreate on them a lot. There's a lot of ice climbing that goes on volcanoes. And here in the United States, the volcanoes of the West Coast in British Columbia, Canada, and then Washington, Oregon, and California, those volcanoes are actually home to a lot of ski resorts. And that's kind of where I used to live. And so I have snowboarded on several of those volcanoes. And some of them are kind of ticking time bombs that could potentially create a pretty catastrophic event. But many of them are what we would call dormant or sleeping. Not a lot of seismic activity happening, and we have no reason to believe that they are a danger to us. Okay, so first off, we're going to talk about convergent plate boundaries. So convergent plates, again, are when plates come together. And I'm going to talk mainly about what happens here in the United States. So on the West Coast, we have that little Juan de Fuca plate. Excuse me, that little Juan de Fuca plate that is subducting underneath the North American plate. And when that happens, a couple different things happen. Okay, so melting is one of them. That subducting plate will go down deep into the mantle, okay? And that subducting plate is oceanic crust, because when the two come together, the oceanic one is always denser. And so it subducts down into the mantle, and when that happens, it drags with it seafloor. It drags with it the ocean water. And what happens when that water comes into contact with that really hot mantle is it lowers the boiling point, meaning that lava, that magma underneath the ground, will actually boil up more readily it doesn't have to get as hot to boil up, okay? So we've got this plate that's subducting down, it's lowering the melting point, and then about 100 miles inland from the coast where those plates are actually meeting, all of that magma more readily boils up to the top. And it creates this chain of volcanoes that we see all along the West Coast. So here's Northern California, Oregon, Washington, and then British Columbia. And each of these little red triangles is a volcano. And some of them are extinct, meaning they don't believe that they will erupt again. Most of them are dormant, and then some of them are just kind of sitting there ready to go at some point. It's just that these volcanoes at convergent plate boundaries don't blow on a very regular basis. It is hundreds of years usually in between each eruption. All right. So it says on the Pacific Rim, okay, so the Pacific Rim would be anywhere along the edge of the big Pacific plate. So it goes, from the western United States up by Alaska and then all the way down on the eastern coast of Asia and around. That is known as the Ring of Fire. And it's called the Ring of Fire because those convergent plate boundaries create a lot of volcanoes. The Cascades are a chain of volcanoes at a convergent boundary where an oceanic plate is subducting beneath the continental plate. Specifically, the volcanoes are the result of the subduction of the Juan de Fuca, Gorda, and Explorer plates. Sometimes these three plates here, this is the Juan de Fuca, the biggest one, collectively are called the Juan de Fuca plate. Okay, so you hear me referring to it as just the Juan de Fuca plate, but there's actually three small little plates that are subducting underneath the North American plate. And again, it is lowering the melting point of the magma, and the magma pops up as these volcanoes that are all along this area. The Cascades have been active for about 27 million years. although the current peaks are no more than 2 million years old. That means that this whole area has been being created and active for 27 million years, but it takes a long time for that magma to build up and create these volcanoes. So the volcanoes themselves are only about 2 million years old. Most of them, because they are far enough north, and because they have a lot of storms in that area, warm, moist air comes in off the ocean. It is forced upwards by the elevation of these mountains. And as that water, that warm, moist water off the ocean rises up due to the mountain, it cools and condenses, and it dumps a ton of snow on that area. So even in California, the mountains in California, they get massive amounts of snow. Therefore, the peaks in that area, these volcanoes, are typically covered by snow perpetually, like year-round, and it has kind of made some small glaciers on top of these mountains. If we look at this map right here, and we'll be doing more work with this particular website. This is kind of it's called a story map of the Cascade volcanoes. So it goes through, and again, we're going to be doing some work with this, but it goes through and talks about each of these specific volcanoes. So here's California, Oregon, Washington, and then up into British Columbia. And you can see that there are several of them. Some have blown in our recent history, in my lifetime specifically, Mount St. Helens in Washington. That blew in 1980, and it was a very large eruption, so large that I remember I was a kindergartner at that time. There was a hazy dust and ash cloud over here in Minnesota. It actually traveled high in the atmosphere all the way over to Minnesota, and it was kind of hazy out, kind of like when there's wildfires in Canada or Montana. We get kind of that hazy effect, and that was true in 1980 from that particular eruption. It goes through, talks about how recent some of these eruptions are. This is right here would be 200 years ago. I think it's 200 years ago. And so you can see that there hasn't been a lot of eruptions in our recent past. Most of those eruptions have happened over the course of thousands of years. 40,000 years, actually. All right. One other thing I wanted to show you specifically today is Glacier Peak, Mount Rainier. Mount Rainier is actually the highest peak in the Cascade Range. It extends 14,000 feet above sea level. Beautiful, beautiful mountain. I have snowboarded on that one. Mount Adams is another big guy. Mount St. Helens. I wanted to show you this little video here within my lecture.
These are the only images that exist of this catastrophic event. But this sequence was not shot by a video camera. Instead, it was created by USGS scientists and graphic artists based on a series of extraordinary still photographs taken by an amateur photographer named Gary Rosenquist. On May 18, 1980, he was standing 10 miles away from the mountain next to local resident Keith Ronholm.
He was on a tripod with a motorized drive and just was... It took a very much time-based sequence. I don't think he was trying to make a scientific record, but it turned out to be a very good record of the event, and I know it was used by many scientists to try to time the event and to measure how fast the landslide occurred.
The landslide, the explosions begin and they get very large very quick. So it helped understand what had happened.
The first frame of the Rosenquist sequence was taken at 8:32 a.m. and 21 seconds. It reveals an intact volcano. But what the image doesn't show is what was happening inside.
Magma was forcing its way up into the volcano, And to make room for itself, it was starting to shove rock aside. So this rock sliding across each other was causing some of these earthquakes. It wants to get out somewhere, and the north side seems to be the weak side. And it starts bulging there. This looked like a big, bad blister on a tire.
Inside, the earthquakes and superheated magma have forced the north wall of the mountain to collapse. The second frame is taken 26 seconds later, capturing the weakened north flank and summit. The video morph shows the mountain collapsing into two huge landslide blocks. 6 seconds later, Gary's third photo shows the top landslide block as it begins to plunge down the volcano. The sequence depicts its movement at nearly 200 miles per hour. Still frame 4 shows the landslide after it has removed the north flank, depressurizing the magma and boiling groundwater. The video morph reveals a series of sudden, violent explosions of gas, steam, and rocks. This is known as a lateral blast. Gary's final frame is taken about 15 seconds later. The lateral blast accelerates to 336 miles an hour, completely obscuring the landslide.
Pause. Okay. So that was the one that happened in 1980 in Washington. And that is definitely our largest, most explosive volcano that we've had in our recent history here in the United States. We'll talk more about the Hawaiian volcanoes in tomorrow's lecture because that is definitely more active on a regular basis, but it's a totally different kind of eruption over there. Let's see if there's anything else. Mount Hood, that's another place that has a couple different ski resorts on it. Mount Jefferson, Mount Washington is actually one of my favorite volcanoes out in that area just because it is so jagged and so tall. It kind of reminds me of some of the views of the Himalayan mountains out there. It is a mountain that extends. You can see it along any horizon out in that area. Beautiful, beautiful area. Wilson. And then we will also, when we're talking about different types, we'll be talking about craters as well, and calderas as well. So there's a few different kinds of volcanoes that we'll be discussing in future chapters. I just wanted to give you a little bit of an overview of what that site was about. So please feel free to check out this site within the book. I will also be posting this particular link in the next few days as we move forward. All right, another place at boundaries where we see volcanoes is at divergent plate boundaries, where plates are moving apart, right? And we've talked about seafloor spreading, where magma comes up and it creates new seafloor. Well, that can build up and build up and build up and build up and build up, and we actually get volcanoes that come up above the sea and create little islands in and around countries that are near a divergent boundary, such as Iceland. Iceland has a lot of volcanic activity. They have a big rift valley because that country is being pulled apart, but along that rift valley, there's also these pilings up of all of this magma that creates these very active volcanoes. And then lastly, we have continental rifting. Okay, so eruptions are found at divergent plate boundaries as continents break apart. The volcanoes in this picture here are in the East African Rift. Okay, so if we look at this picture, this would be northeastern Africa. You can see that this part of the country is actually being ripped away from the greater land of Africa. And that is because there is a divergent boundary right here. It is ripping Africa away from Saudi Arabia and then also taking this entire area off of the continent. And you can see here that these little arrows show, by how much it is moving. every year, how many millimeters per year. And it's the same thing as in Iceland. You know, these two plates are moving apart and magma is coming up and it's piling up and piling up and piling up, and you get these big mountain building events that are active, right? Because the plates are moving and magma is coming up. And so you get a volcanic chain along here as well. All right, so wherever there is divergent boundaries along the divergent boundaries along continents, you are definitely going to see volcanoes as well. Okay, so convergent boundaries where one is subducting, we get lots of volcanoes. And then another place would be at divergent boundaries where they're pulling apart. Most often what we see there is seafloor spreading. But also at the same time, if it's not deep in the ocean, you know, if it's deep in the ocean, we get underwater volcanoes. But if it's near land where the water isn't quite as deep, where the seafloor is not so far away from the surface of the water, we get pilings of lava that create mountains and that are active volcanoes. Okay, so we see that in Africa, we see that in Iceland, and then again we see lots of volcanoes along subduction zones where plates are converging. Okay, so we are going to talk. We're going to talk more about different types of volcanoes. We're also going to talk about the Hawaiian volcanoes tomorrow, and I'm going to post a little video about what happens at subduction zones. Okay, again, that is where the Cascade Range of British Columbia, Washington, Oregon, and California, those are all in a subduction zone. And so I'll post a little video that shows you exactly how that subducting creates chains of volcanoes along those zones. And I will talk to you soon.